at least the normal face-to-face, I can see you, you can see me, and I can see that you're like actually here and at least pretending to do work. But as Ms. Delvo said, every day we have to kind of trust that you're paying attention anyway, so is it really that different when you go home? Well, the temptations are way different, but technically it'll be a choice just like it always is, to not just be here, but to be engaged and to be listening and to be trying to learn. So hopefully you choose right today, or at least choose to the best of your ability. And if you're sleepy, just ask someone to keep poking you during class. Boop, boop, boop. All right, here we go. I have some of the deadlines. I have some of the due dates. You guys have already written this stuff down. I have the calendar. We can look at that later. Sequences and series. What are they? Well, sequence first. Section 9.1 in some ways is the hardest section of the entire chapter. In some ways. 9.5 is, no, 9.4? 9.4, I think, is the most fun. Maybe 9.3. Oh, just kidding. One of those is the most fun because it actually lets me introduce a really important topic in calculus, which I find to be fun. But we're not there yet. 9.1 is a little annoying because it is basically the general, here's what they are section, and you're going to see nice ones, you're going to see nasty ones, you're going to see like, hey, just make up a formula for this ones. And you're like, huh? That's not my job. I don't make up formulas. I just try to plug into them. Anyway, so 9.1 is going to be messy at times, so I'm going to try to point that out to you when it happens. And you guys will do your best on it. Just realize it's a big old fat introduction section that can be kind of messy. Let's just get the main idea, yeah? So sequence, set of values. Matrices, it was a rectangular array of values where you had a common characteristic across and a common characteristic down if you were actually applying them. Sequences is just a list, basically, a list of values. List of values separated by commas. It can be a list of objects, technically it can be a list of other things, but we'll just say a list of values for right now. I would say finite values, but what do you see right here? Ooh, could be infinite too. But usually for us to deal with them, maybe we are going to infinity this chapter. Usually we cut it off and we say, okay, all right, the first 5, the first 10, the first whatever. But sequences can go on forever, but they can also be cut down. But if they are cut down, then we're going to talk about them as the nth, well, let's not say the nth term. Not worry about what we're going to call them quite yet. But let's go ahead and zoom in on a sub n. So a sub n is this little guy who's the general term. I want you guys to go ahead and name him the general term. Sure, not that one. General term. As opposed to specific terms? Yeah, A1 is a specific term. He's the first guy, whoever he is. A2, A3, A4. AN is supposed to be the nth term. Here he is, another way of defining him. The general term or the nth term, and he kind of shows the pattern. He shows the pattern. So if I have the first, the second, the third, the fourth, the nth term says, where are you getting all of these from? Which can make it really hard because then the nth term is supposed to be a formula that somehow encapsulates all the ones up here. And specifically the ones for what if n is 1, what if n is 2, what if n is 3, what if n is 4. Oh, stink. It's a formula where you plug in an n and you get out a number. It needs to be the special numbers that you see. Hence the creation of formulas. But describe what you see. Domain of sequences is kind of weird because it's only integers. Wait, does your brain realize why that's weird? Only integers. What numbers are positive? Okay, it says positive integers. Hold on. Positive, that's just like a characteristic. Whole numbers. Yeah, 1, 2, 3, 4, 5, 6, 7. Now, it can start at 0 sometimes. I think in pre-cal, we mostly start at 1. In calc, we kind of go back and forth between 0 and 1. Once again, calc BC, not AB. We can kind of go back either way. If you're in, I don't know why you'd be doing this in physics. Oh, you might. We would start at 0 sometimes because t, time equaling 0, is the beginning of the situation. But if you're talking about like an object or a list of objects, the first one is the first one. So we go get back and forth. But if it's only like 0 and 1 and 2 and 3 and 4, what would the graph look like of the nth term if you are only plugging in 1 and 2 and 3 and 4? Linear. Well, no. It could be linear. Could be going up. Could be going down. Could be swooping. Could be like changing. I don't know. The numbers can be doing all kinds of things. Will it be connected? Oh. Because when you connect graphs, aren't you getting everything between 1 and 2 and 2 and 3 and 3 and 4 and 4 and 5, the 1.1 and the 1.7 and the 1.9 and everything in between? So if it's just 1, if it's just 2, if it's just 3, what's it going to look like? Yep, and it's called discrete. These are discrete functions. Anyway, we might talk about that term more later. It might just be something from way higher up in math that I just threw in. But this is called a discrete function. Because it's like a point and a point and a point and a point. It's not connected. Hey, questions can be as easy as this. You see how easy this is? If it helps, you could think of this as being a of n. We don't write it like that, but you could think of it like that. You could think of it like a of n, but we write it a sub n. It's more like it's named the nth term, even though okay, it's kind of like a function. But what is the first term, guys?
1.
Why?
Because it's a 1.
Yeah. Oh, yeah. Okay, so, yep, plug in 1, you get 1. What's the second term?
2, so you get the 1.
Yep, what's the third term? What's the next term? Hey, could you keep plugging in? Sure. Or could you see there's a pattern? What's the pattern?
3.
Every time you're adding 3. Now, wait a minute. If the pattern is every time you're adding 3, does anybody remember that's called an arithmetic sequence? You could say arithmetic, and I go both ways. I'm not exactly sure. Arithmetic, I think, should be spelled differently. But Ryan Murphy from a few years ago could have sworn that was the right way. And I said, okay. But anyway, sounds arithmetic. But anyway, it's that guy that you add the same thing over and over and over and over again. It's actually called a common difference. Don't worry, all stuff that's coming in section 9.2 when we get specific to special types of sequences and series. So here's the weird thing. Do you guys see the plus 3 in the nth term formula at all? No. Why isn't it there? Can't we just say n plus 3 and it'll work? 1 plus 3 would be 4. 2 plus 3 would be 5. 3 plus 3 would be 6. That would only add 1. I can't just do n plus 3. How does this formula result in adding 3 every time?
Because of actual thinking. There's -2.
There's -2 is a constant. -2 is a constant, but that doesn't actually get me my plus 3. That actually just gets me my first starting point. What's actually causing there to be an additional 3 every time? You guys know what multiplication truly is? 3 times 1, 3 times 2, 3 times 3. Multiplication is repeated addition. 3 times 1, 1 of the 3's. 3 times 2, 2 of those 3's. 3 times 3, 3 of those 3's. 3 times 4, 4 of those 3's. Multiplication is how you get a repeated addition. So when I say 3 times n, there's 1 of those 3's. 3 times 2, like increase n to 2. Now there's 2 of those 3's. 3 times 3, 3 of those 3's. 4, I'm adding, check it, it's weird. By having 3 times n, I am, each time my n goes up, I am getting an additional 3 in there. It's weird. Multiplication gets me addition? Yeah. Oh, so what if I need to multiply? Addition comes from multiplication. What did multiplication come from? Excellent. Ooh, nice. All right, look at that. Well, that's fine. Just kidding. Oh, it moved. Okay, so defining sequences. Formula for the nth term. So we have a sub n. We can also think about it as I've already written in case it helps. A of n. It's a formula that says give me n and I'll give you your number, but it's a little bit hard sometimes to know how to make it. Sequences are given A1, A2, A3. It's helpful for us to identify a pattern. That's helpful. That's helpful. If we're moving recursively, I'm just going to say for recursive right now. If we're moving recursively, what's that word mean? We'll get to it. If you know a computer programmer, ask them about recursive formulas or recursive programming. Anyway, identifying a pattern is really helpful for recursively looking at something. Something like a computer could do recursive steps really, really fast, whereas it would take us a long time. But it will also be helpful to think of terms as related to n for explicitly defined things. And we'll get to what those terms mean in a little bit. So what I need you to realize is seeing the pattern isn't necessarily the same thing as trying to get your A sub n formula. Seeing the pattern is good and all, and it's good for a certain way of dealing with sequences or for certain things that could be asked of you. However, it might be helpful separately to think of it in another way as well. As far as, okay, how could this term come from n equals 1? How could this one come from n equals 2? How could this one come from n equals 3? How could a 1 be plugged in to get that? How could a 2 be plugged in to get that? How could a 3 be plugged in? Ah, stink, and I need it all to be the same formula? Anyway, it's tricky. It's tricky. Once again, this is just an intro section. To be honest, not even Calc BC kids have to work that much with making their own formulas. A little bit, but not a lot. Let's go ahead and dual page and go forward one. This is an example of one of those nasty questions, but if you guys notice, number 1, this isn't until number 30 in your homework. And this is asking, can you find a pattern, number 1, but number 2, and possibly separate from the pattern, can you think of how could you plug in 1 to get 0, plug in 2 to get 3, plug in 3 to get 8, plug in 4 to get 15, etc. But first of all, what's the pattern? That was usually the easiest thing to find. Yeah, one way is I'm adding 3, and then the next time I'm adding. Yeah. So if I was to ask you guys for the, let's see, 1, 2, 3, 4, 5. If I was to ask you for the 6th term, couldn't you just use the pattern and say I don't even care about them? Right? Yeah, I would just add 11, and 11 would give me 35. No big deal, right? The pattern can be really helpful for recursive, which means just jumpity jump, jump, jump. Okay, that's a silly way of saying it. But recursive means you're just kind of going to the next, to the next, to the next, to the next. I don't even know where I've come from, but I do know how to get to the next one. I don't know how to jump way into the future, but I do know how to get to the next one. Recursive is basically just how to go step by step by step by step by step. But do you see why that would be a dilemma if that's all we knew? What if I wanted A sub 100? Either figure out how to program a computer to do it for me. Either program how to make a computer do it for me, or jump a whole lot of times and try to keep track. Or figure out another way to get there. Now, there is a way to recursively define a sequence, and we might see it a little bit in the future as well. I could say, to get to a term, I start with the previous term. This is a little weird, but the 7th, this would be the 6th, the 10th, this would be the 9th, the 3rd, this would be the 2nd. Whatever place I'm in, this would be 1 before it. And then I could say, you're adding. Yes, you are adding. And you're adding these odd numbers. Odd numbers. N. Nope, that'd be 1 and 2 and 3 and 4. 2n. Oh, nope, that's 2 and 4 and 6 and 8. 2n minus 1. Wait, 2 times 1 minus 1 would be 1. No. 2n plus 1. 2n plus 1? If n is 1, 2n minus 2 would be even. Careful, I need to make odds. So if I start at n equals 1, oh, nope, I need to get to the second term first. Just kidding, I was 2n minus 1. The 3. There we go. If I start at 0, if I say you're starting at 0, then to get to the second term, I use the first term, 0 plus, and then I do 2 times 2, because I'm in the second term. 2 times 2 is 4, 4 minus 1 is 3. So when I get to the third term, I use my second term, 3, and then I add 2 times 3 is 6, 6 minus 1 is 5. To get odd numbers, I can always do 2n, which is an even, plus or minus 1. I just need to think of, am I getting a higher or am I getting a lower? And that could actually get you each of these guys and each of these jumps being like, okay, I started at 1, but to get 2, I use 1, but I use the n equals 2, 4 minus 1 is plus 3. I know I'm going fast. I'm just showing you, don't worry, we'll work with it more. A recursive way of saying, hey, computer, can you take this pattern and go to the hundredths for me? And there's a way in a mode of your calculator called SEQ, sequence mode, to actually type this in. Calculator's out. We have time. Let's look at it.
Miss, do you think you get the 2n minus 1?
Well, see, I've done a lot of these, and so I've learned that anytime you have a 2n, you can get all the evens. And if you get all the evens from 2n, where are all the odds with respect to the evens? Right above or right below? So if I take 2n and add 1, I'll get all odds, but I'm going to get all odds 1 above whatever even I have. If I do 2n minus 1, I'll have, like, so, for instance, in this one, recursive always needs a starting point, because I could be adding 3 to, like, -7, and it would look totally different. So I needed to tell it where to start. You're starting at 0. But then I needed, okay, so to get to the second term, so I was already on n equals 2 to get here. So I knew I needed 2 times 2, 4. I needed to go down 1 from that to get my plus 3. And then at 3, I'd be plugging in 6 minus 1 would be 5. That would get me my plus 5. At 4, 8 minus 1 would be 7. So, but I could have also done plus 1 if it started with like 5 and 7 and 9. It could be plus 3 if I wanted 7 plus 7 plus 9 plus 11. So I just kind of make the minus or plus an odd number to get to the right odd to start, and then it will start jumping. But I just know 2n is always even.
If it was an even, I wouldn't have to have it.
No. No, you just do 2n. Or 4n or whatever, like whatever you want. So check it. I said mode, right? Okay, mode. Pre-cal, they're doing determinants and inverses. Okay, mode. You guys see the SEQ mode? There's function. We're going to see that one in a little bit. Different chapter. That one in a little bit. Different chapter. Okay, this one. SEQ. Aw, they don't have A's. That's okay, they have U's. They do them, whatever. We could call it U's, but we're going to call it A's. That's more mathematical.
Wait, how do you use it?
Mode. Boop. Hit the SEQ button.
Yeah, I did.
And then you go your Y equals. You go your Y equals. Okay, so, do you guys see U of 1?
Yes.
That's my 0. Okay, U is like A. I know it's weird, but it is. Okay? U1 equals 0 because that's my starting point. Now, I can, check it. Do you guys see 7 and 8? Look above, 7 and 8 in blue. Don't they have little baby U's and V's and U and V and W? 7, 8, and 9, the little lowercase U and V and W is for this mode. I can do second 7. Second 7.
Mine doesn't have the U1, it has the N and then the UN.
Yeah.
But you should have a U of and min, right?
Yeah.
And what's, check it, ready? What's the U of and min the same thing as? Yeah, your U of and min is U of 1. So you guys go ahead and put in 0 to your U and min spot.
So what do I do with the UN spot?
Oh, well that's what I'm doing right now.
Oh, okay.
Second 7 gets you your little baby U, because we're going to say, hey, you can take the guy from before, see, a sub n minus 1, u of n minus 1. Calculator, you need to take, for 2, you need to go look at 1. And for 3, you need to go look at 2. And for 4, you need to go look at, it'll do it. You're telling it to look at the previous one. Plus, oh, it's just the X button. Do you see how X is also an N sometimes? Oh, hey, all these little guys on the X button. It's the same thing as, that's the X, that's the T, that's the theta, and that's the N.
Oh.
Ooh, snazzy. We're learning our calculator now. 2, N is the X button, minus 1. Now, go to your table. Oh, let's make sure everything works. 0, 1. Let's just do automatic. 0, 3, 8, 15, 24, 35, 48, 63, 80, 99. Could I just scroll to the 100th one if I really wanted to?
Yes.
Yeah? Is there a better way?
Just writing them.
Can you guys ready? Can you vars, y vars, oh, there's no sequence. Hold on. Can you do u of 100? Just kidding, not even that hard. I didn't need to go to bars and all the crazy stuff. Second, 7. Gee, this is cool. You go to the 100. U of 7. Sorry, second 7. U of 100. Oh, can I have the calculator go like crazy high and do crazy stuff that I would never want to do and go to the 5,000? Why is it taking so long?
Because it's calculating.
It's going to the 5,000. Is it going to get there? Yeah. Is my calculator super fast? No. Does it have as many gigs as your iPhone? No. Okay, give it some time. It got there. Now, if you go crazy high, like the million, is it going to take a while? And it might eventually be like, you gave me too much. I'm just a little calculator, okay? Strong calculator, way stronger than any calculator in the past, but still. Yeah, it's gonna take some time. It's gonna take some time. It's okay. It's okay. It's okay. If for any reason your calculator ever, like in calculus questions, sometimes people try to make it do things it wasn't meant to do. You can always hit the on button. The on button actually breaks the code and says stop. You do the on button and quit and just be like, never mind. I don't really need the 5,000. Sorry, little calculator. Pet it a little bit and then here we go. But guys, you can also do this thing. You can also do the table setup. You can also do ask. And remember, you can type in whatever you want, like the, hey, I want the 5th, I want the 9th, I want the 100th, right?
Wait, how did you do that?
Oh, remember how the table, we can make it ask us? That was from the graphing calculator handbook, I think. We can make it ask us, and then remember, if you don't like whatever's in there, you can always delete out. So that one's cool too, but this notation, the function notation, is pretty simple. So, all of that to say, come back. With technology, is this whole recursive thing kind of cool because it can do the steps for us. Yeah. And didn't you guys see the pattern pretty quick? +3, +5, +7, +9. You had to learn how to write an odd number, but it's not too bad. But what's the problem that it was actually asking us to do? The pattern or the formula? How could I plug in 1 to get 0, 2 to get 3, 3 to get 8, 4 to get 15, 5 to get 24? What kind of formula would give me these types of numbers by straight plugging in? Not jumping, straight plugging in. He wants to figure it all out. If it's a special type like 9-2 or 9-3 that always has the same pattern of like +3 or ×2 ×2, yes, but it actually comes from the pattern. This one, it's always changing.
But it has the same second.
Has the same what?
Second.
What is that?
2.
Did MC, there's 2 apart, 2 apart, 2 apart. Wait, constant second differences. That wasn't linear, because linear was always adding. That wasn't exponential, because that's always multiplying. What is the constant second difference? What type of table is a constant? It's a quadratic. No? Caitlin, Sophia, you don't remember constant second differences in tables last year? Linear was add. Exponential was add, multiply. Quadratic was add, second difference. Quadratic? How is this a squared? I don't get how it's a squared.
N squared.
Almost n squared. Isn't it n squared minus 1? What's 1 squared minus 1? 0. What's 2 squared minus 1? 4. Minus 1 is 3. 9 minus 1, 16 minus 1, 25 minus 1, 36 minus 1, 49 minus 1. So was there a pattern to give us a hint as to what type of equation to make? Yes. The first time anyone's ever seen the constant second difference. Or realized what it showed. Or at least hinted in the right direction. Look at that when brains come together. N squared minus 1. What does that mean? If you wanted to find the 100th term by hand, would you guys really want to jumpity jump in your calculator by adding a bigger and bigger and bigger odd every time? Maybe. But wouldn't it be nicer to know that 100 times 100 is 10,000 and 10,000 minus 1 is 9,999? I went there by the time. But is it kind of hard to make those formulas sometimes? Yes, which is why that is not the main point of this section. It's not like how amazing are you at making formulas out of nothing. Oh, okay, there was a constant second difference. It's a quadratic. But still, is that the main skill of this section? No, it's just to show you. It's just to get you exposed to sequences and series and remembering the basics. Will there be a few questions like this to try to get a formula? Yes. If you can't find a formula, ready? Can you try to define it like a programmer would in a recursive jumpity jump jump? If you can't do that one, try to do that one. Still helpful, still useful. But do you guys see somehow or sometimes you might have to double check you have the right formula? Oof. Is this one just 1 over 2 to the n, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4? Or is he a bit more complicated? Let me zoom in because he's a little bit zoomed out. Laura, what's up, kid? Oh, sorry. Making that stuff. You see how they are so similar, but eventually they, snazzy terms. Can I say diverge? I shouldn't say diverge. That's a little illegal. Ask the calculus BC kid why I stop it. But anyway, they're going to go separate ways. Anyway. Do you see the difference in their formulas, though? Am I expecting you to make that up? Nope. Not even close. But do you see how 2 could be very similar, so we have to make sure we have enough terms to check that we have the right formula. That's just to be careful. You don't even necessarily need to write it down. But do you see the other pattern of 2 to the 1, 2 to the 2, 2 to the 3? That's going to be to the n. How you have the same base, but just higher and higher powers. Anyway, lots of patterns. Hey! Guess what this is? What I already showed you. Guess what this is? What I already showed you. So defining that whole recursive thing to end off class today, we'll end here. Explicit is that a sub n squared minus 1, jumping straight to the 100th term with a formula. Recursive says, there's a pattern. Let's describe them. There's a pattern. I've already said some of this stuff out loud, just getting it down. How to progress, how to go to the next, to the next, to the next. Pros is it's usually fast to find the pattern. And once you learn how, and to program, you can find the pattern. You can, if you know how to program it, like I kind of showed you in your calculator, it goes pretty fast. The cons are, it's going to be hard by hand. Okay, not for like the next term, but like for the 100th, 1000th, 5000th term. Like, no thank you. I don't want to do that by hand. Hard by hand. And you could even say, depending on the strength of your calculator or your device that you're programming to do it, it might take it a while. Oh my goodness, that's not annoying at all. Now you could use n, you could also use k, but guys, here's a dilemma. When you program, you need to make sure, when you write it out, you need to make sure that you're defining like a next in terms of a previous. Sorry, that should be a -1. There's just no way for me to actually get my equation editor to do that -1. But like in Algebra 1 does this? Kind of. In Algebra 1, to get to the next term, or you could also think the current term as far as the current n term. To get to the next term, the current term, we are using the previous. Fibonacci. Hey, I have tons of fun Fibonacci videos. If you guys need some extra enrichment if you're home at some point. All right, cool kids. I'll see you later. Bye, heart. Queen. See you guys later. Be safe out there. Come ask me if you have any questions. Otherwise, I'll see you when I see you. Today I have a meeting at like 3:30, but I'll be back in my room a little bit after that. It might be open. It might be